All right, so my aim is to talk about discrete logarithm problem. But in the discrete logarithm problem, the hardness of the problem depends on the group that we are working on. And by group, we are talking about algebraic groups. So in order to understand what the discrete logarithm problem is, first, I need to give you some basic algebra. So these are very basic definitions. I'm going to give you the necessary algebraic knowledge and some examples about them. So let's start with a group. Here, of course, we are talking about algebraic groups. A group G in algebra is a set of elements together with a binary operation star on G that combines two elements in G and form a third element in G, satisfying the following group axioms. So let's start with it. First, we want it to be associative. This means that first B star C, then A star the result equals to A star B, then star C. Okay, this is associativity. We also need an identity element for a group. So if E is the identity element, then it should satisfy the following equality. A star E and E star A should equal to A for every A in the group G. Okay, not for a single element, but all of them. And every element should have an inverse. So B is an inverse of A if A star B or B star A equals to the identity element. Okay, so if you have these three properties, associativity, identity, and inverse elements, then we call it this set and this operation together with this operation a group. So let's give an example. Integers and the addition operation is a group because it satisfies the associativity, right? Because in addition, these two results are identical. 0 is the identity element, because if you add 0 to any number in Z, the result will be A anyway, right? And every element has an inverse. If you choose an element A in the Z, then it has an inverse minus A, because A plus minus A would give you the identity element 0. So this is a group, okay? As you can see, we have to define the operation here. So we don't call a set a group, we call a set together with an operation. Okay. Let's give it another example. So because once you give this definition, you start to think that almost everything is a group, right? So let's give an example. Z star, here I said star because I'm removing the 0 element. Okay, this is just a common notation. And if you use the operation as multiplication, then this is not a group. Let's start. It satisfies the associativity, right? Because both of them equals to just A times V times C. There's the identity element, which is 1, because if you multiply any number A with 1, the result will be A. Recall that A cannot be 0 because 0 is not in this set. So we have the identity element for multiplication. But the problem is that not every element has an inverse. Actually, only the element 1 has an inverse. Other than that, just take a random A from this set. And we need to have a number here so that multiplication should give the identity element, right? So if you have A, the inverse should be 1 over A. But if A is different than 1, then 1 over A is not in Z star, right? So this is a problem. So not every element has an inverse. So it is not a group. Okay. But if you move on to rational numbers, remove with, of course, you remove 0 because of this star. Then multiplication is a group here, because now we have the inverse element for every A. So as you can see, the very basic definition. So we actually seen an example where we have a group with the addition operation, where we have the multiplication operation. Now we are going to talk about, combining both and so on. Okay. Since we are going to represent digital data as group elements, we mostly focus on finite groups in cryptography instead of infinite groups. So this is important. So most of the time we will be focusing on ZP, where P would be most of the time a prime number. But in this example, we have Z4 and the addition operation. So this is a group where Z4 is, the number starting from 0 to 3. So here we are talking about actually modular arithmetic. So it has associativity because these additions both equivalent to the same thing in modulo 4. There is an identity element 0. If you add 0 to A, it becomes A modulo 4. And every element has an inverse. Let's start. 0 is its own inverse because it is the identity element. 1 has an inverse of 3 because 1 plus 3 equals to 0 modulo 4. 2 has inverse of 2, so it is the inverse of itself. Since we found the 3 as the inverse of 1, 1 would be the inverse of 3. Okay, so every element has an inverse. So Z4 with addition operation is a finite group. Okay. So this is somewhat, by the way, counterintuitive for mathematicians, because in every algebra class or field classes, lectures, you will see that mathematicians are always working on infinite groups or infinite rings or fields. This is because most of the time, those parts are the interesting parts, okay? They barely talk about finite fields most of the time. But in crypto, we need this finite groups. This is why we are actually interested in this kind of groups, okay? Again, Z4 star with the multiplication is not a group because not every element has an inverse, because if you choose 2, you wonder if it has an inverse. So multiply it with every element in this group, in this set, sorry. So multiply 2 with 1, 2 with 2, 2 with 3. So you multiply 2 with every element in this set, and none of them gives you the identity element 1. So this means that it doesn't have an inverse. So you might think why this is the case, but this is kind of obvious because here working something modulo 4, which is an even number. And 2 is also an even number. So you cannot have, multiplying 2 with some number, then dividing it 4 and, have the result with 1. So this is why not every finite group, finite set actually is a group with respect to multiplication. And 2 has no inverse in this set because the greatest common divisor of 2 and the modulus 4 is not 1. So they are not relatively prime. Then let's give an example where this is the case. So let's think about ZP star and with multiplication operation. This time I'm going to say that this is a group, but I'm fixing P as a prime number. Okay. So ZP star is a set where it starts from 1 to P minus 1, and P is a prime number. It satisfies associativity. We have the identity element 1, but we also say that every element has an inverse because the greatest common divisor of any element with P, any element in this set which is less than P, so greatest common divisor of any element from here and P would be 1 because P is already a prime number. Nothing less than P can divide it except 1, right? So this is why every element has an inverse. So this actually, I'm not proving it, but I'm giving you as an actual fact. This comes from number theory too. So ZP star is a group with respect to multiplication when P is a prime number. These are the things that we are going to work on. Okay, so let's talk about the generator of a group. So the small g is called the generator of the group G if every other element of the group may be obtained by repeatedly applying the group operation to G. Each element can be written as a power of G in multiplicative notation. Each element can be written as a multiple of G in additive notation. So again, let's give an example to make this definitions more clear. So as an example, I'm saying that 2 is not a generator of Z7 star with respect to multiplication. As you can see, 7 is a prime number, so this is really a group. But 2 is not a generator because let's start multiplying 2 with itself. So I'm using the group operation on 2. So I'm taking 2. So the power, first power of 2 is itself. Then I'm multiplying 2 with 2. The result is 4. Then now multiplying 2 with 2 and 2. So you are actually multiplying 4 with 2. The result is 1. So I obtained the identity element. If I continue further, I would be actually repeating these two values, right? Because 2 to the power 4 would mean that 2 times 1, which is 2. Then I will end up with 4, 1, 2. So if I keep multiplying 2 with itself, this part will be 2, 4, 1, 2, 4, 1, 2, 4, 1. But the problem is that I'm saying that this is not a generator because a generator should generate all of the elements in the set, in the group, but it does not. So let's give an example as a generator. So I'm saying that 3 is a generator for this group. So let's start and see that, starting with the first power to the 6th power, you realize that I'm actually generating every element in this group. So 3 is a generator. So actually, since there are 6 elements in this group and 3 generates all of them, we say that 3 has order 6, but 2 has order 3. So the power where it gives you the identity element is actually the order of the elements. Okay. So not important for this course, but it is no surprise that the order of an element divides the order of the group. This is actually a theorem from algebra, but not related to our course anyway. So you can also ask a question here. Okay, 2 is not a generator, 3 is a generator, but does this mean that 3 is the only generator? The answer is not always the case. Maybe 4 or 5 is also the generator. I mean, 4 most probably is not, as we can see from here, but probably maybe 5 will be a generator. So there can be more than one generator for the same group. Okay. Okay, moving on to abelian groups. A group G is said to be abelian if x star y equals to y star x. So we are actually talking about commutativity here. So, the order of the elements shouldn't change the result. So if you think about regular mathematical operations like addition and multiplication, this is always the case. So you might think that this is always the case? Isn't every operation like this is a commutative or abelian in this definition? The answer is no. Think about matrix multiplication. If you change the order, the result will be different. Okay. So with this definition, we are moving on to rings, and I will talk about fields. A ring R in algebra is a set of elements together with 2 binary operation plus and multiplication. So in the groups, we were talking about a single operation. Now I'm having both addition and multiplication. And this should satisfy the following. R should be an abelian group under addition, and it also should have associativity for multiplication as follows. Also distributive properties where the multiplication is actually distributed over the addition. Okay, as you can see. So this means that A star B plus A star C and so on. Okay, if you have these two properties together with being an abelian group, then we will say that R is a ring. Examples: Zn with respect to plus and multiplication is a ring. And again, here this is a finite ring. This is an infinite ring, Z plus and multiplication, because the multiplication has this distributive property over addition. Here, the important thing is that we are not looking for the multiplicative inverses. This is why these stuff became rings, which were in groups with respect to multiplication here at like Zn. Okay. So moving on to the final definition, field, which we are actually was trying to reach. A field is a set F which is closed under 2 binary operation plus and multiplication. And F is an abelian group under addition. Also, F star is an abelian group under multiplication. So now we are looking for 2 group operations at the same set. Here's an example. ZP plus and multiplication is actually a field when P is prime. So generally, we use the F notation here to denote as a field. Electrical engineering people prefer to call it a Galois field. These are the same thing when P is a prime number. Okay. Of course, being Galo is somewhat a different definition, but if you're interested, you can look at a algebra course. But here, know that this is the thing that we are going to work on. Okay. Finite fields, most of the time we are looking when P is prime. Okay. But more importantly, we said that when this P is not prime, we cannot guarantee that it is always a group or a field, right? So question is, are there any other finite fields where P is not prime? The answer is yes. If Q is a prime power, then there's essentially only one finite field over a finite field of order Q, which is denoted by FQ. So this means that you have a field when P is prime or it is a prime power, like 3 to the power 5, which is a prime power. Okay, so this is important because all of the definitions of fields, elliptic curves, and so on actually are defined over this kind of finite fields. Most of the time, either we are going to choose Q equals to P, which is a prime number, a very large prime number, or we will choose Q as 2 to a huge number like 100 or something. Okay. You can also choose other prime powers like 3 to the power something, but this actually gives a lot of options. So for this reason, in cryptography, either we stick to the prime number P or to the power of 2s. Okay. So these are the main definitions that you are going to need when you're working on public key cryptographic algorithms.